So this slide shows results for the 6 samples. Final fitted models for concurrent cost prediction in indemnity, PPO, and POS, and for prospective cost prediction. And so you can see the number of terminal nodes which range from 6 to 12 in all but one of the models. And this was optimal. And the percent of variance explained in the concurrent cost prediction was around 50%. And in prospective, around 15 to 18%. And these are numbers that this is typically what one sees in the literature for various different risk adjustment systems, even for those deterministic sorts of systems that I described earlier. Although it's somewhat, one has to be cautious, obviously, comparing these results in one population to results using some other system in another population, because the variance in the population that is being studied obviously affects how much variance can be explained. And then that is compared to the results of the main effects models, which show increases in absolute terms of 2 to 7% for the concurrent prediction, about 1% for prospective. So in relative terms, about 10% improvement. So clearly, there is a value. The interactions that one is able to discern with boosted trees that cannot be discerned with main effects do provide additional information. And I think it's obvious this model here with only 2 terminal nodes doesn't model any interactions. So in this case, for prospective cost prediction in the POS plan, there wasn't any apparent value in modeling interactions. The best fitting model had 2 terminal nodes per tree, 1 split. So I've suggested that in terms of interpretation of the final models, that what we find in tuning in terms of the best fitting number of terminal nodes tells us something about the upper limit on order of interactions that might be important or might be influencing cost predictions. And we can also look at relative importance. Essentially, one gets at this by beginning with the sum of Huber loss across all nodes that split on a given independent variable. And you do this for all 264 independent variables. And then starting with that point, you can derive a relative importance or relative influence on overall model fit for each of the predictors. And so here shown as an example are just the 30 of 274 variables with the highest relative importance for 2001 cost prediction. What is shown is a comparison of the relative importance for 2001 or concurrent cost prediction versus for prospective. One can see that the most important variables, not surprisingly, are the indicator variables for very severe, complicated medical and surgical conditions, ones that one would often require intensive care or multiple procedures. So we have patients who have respiratory failure and have been on ventilatory support, have had a complication of the complication of device. Oftentimes, those are cardiac procedures, valve replacements, and so forth, coronary artery grafts. For prospective prediction, the same variables tend to have relative importance, but it's more subdued. And interestingly, chronic renal failure is more useful for prospective prediction, which is not surprising, and age. So in closing, I think it's safe to say that this regression, what I'm calling regression tree boosting approach, or with this tree net with tree type equal regression, was able to find consequential interactions among diagnostic groups and incorporate them automatically into risk adjustment models that were customized to populations under study, the essentially 6 populations that we just looked at, if you will. It appeared, although we have to be cautious about comparing this with other systems used in other populations, but it appeared to explain healthcare cost variation roughly comparably as well as deterministic modeling approaches that have been reported in the literature. And then sort of going back and sort of reviewing some of my earlier comments, I think it's fair to say that algorithmic modeling compared to deterministic modeling involves fewer assumptions, you could say no assumptions, about cost effects of interactions among diagnoses. It allows the data to speak, if you will, via the algorithm. It's clearly less costly. I did this myself. Obviously, these risk adjustment systems involve scores of researchers working together, scores of physicians. It's, I think, more readily adapted to new populations and new conditions and changes over time. So at the back here, I've just listed some references. And thank you very much.